St. Louis, Missouri, late summer 1904. A series of percussive booms echoed across the manicured grounds of the Louisiana Purchase Exposition, a sound more suited to a battlefield than a World's Fair. The sharp, rapid reports, like a volley from a battery of light artillery, drew curious crowds away from the monumental Palace of Agriculture. They gathered not for a military reenactment, but to witness a demonstration that would fundamentally alter the American breakfast table. There, a botanist named Alexander P. Anderson stood before a row of 8 bronze-barreled cannons. But these were not weapons of war. They were his patented puffing guns, each one containing not gunpowder and shot, but simple grains of rice. Heated to immense pressure and temperature, the guns were aimed into large wire cages. With a sudden release, they discharged their contents with a deafening crack, firing not projectiles, but a billowing white cloud of puffed rice. Each grain exploded to more than 8 times its original size. What the crowd witnessed that day was far more than a novelty act. It was the public unveiling of a radical new industrial food process. The impact of this food shot from guns would prove as transformative as the violent physics that created it, shattering assumptions about food processing and creating an entirely new category of mass-produced, shelf-stable goods. The story of this revolutionary breakfast cereal begins not in a kitchen or a baker's oven, but in a laboratory, with a scientist who applied the principles of thermodynamics to the cellular structure of starch, effectively weaponizing steam pressure against the grain itself. To understand the industrial-scale forces that Anderson's puffing guns would unleash, one must first examine the strategic dilemma they were built to solve, the state of the American breakfast at the turn of the 20th century. For the nation's rapidly urbanizing population, the morning meal represented a fundamental conflict between agrarian tradition and the logistical demands of modern life. The dominant option was a heavy, protein-centric meal, a direct holdover from a farm economy that required thousands of calories for manual labor. A typical breakfast might consist of fried beefsteak or pork chops, potatoes, eggs, and heavy breads or biscuits, a preparation that could demand over an hour of active work over a coal or wood-fired stove. This was a significant logistical burden for the urban household, which operated on factory whistles and train schedules, not the rising sun. The alternative was a tactical retreat into monotony. For those seeking a faster, shelf-stable option, the choice was typically limited to a rotation of boiled porridges. Oatmeal, cornmeal mush, or farina could be prepared relatively quickly, but they offered a repetitive and uninspiring experience. Early health reformers like John Harvey Kellogg and C.W. Post had identified this opening, fielding the first wave of cold, ready-to-eat cereals. However, these initial products were imperfect weapons in the war on breakfast inefficiency. Kellogg's first flake cereal, Granos, was introduced in 1895 but was viewed by the public as health food, while Post's Grape Nuts, launched in 1897, became notorious for a tooth-threatening hardness that often required soaking. These early cereals proved the concept, but they lacked mass appeal. The result was a vast, unserviced market. A strategic gap had opened between the time-consuming perishable farm breakfast and the bland, unexciting gruel. Millions of Americans, clerks, factory workers, managers, and their families required a meal that was not only fast and shelf-stable, but also light, digestible, and most critically novel. The arithmetic of the modern home, with its smaller ice boxes, shrinking preparation times, and a workforce shifting from the field to the office, demanded an entirely new doctrine for the morning meal. The problem was not a lack of food, it was a fundamental mismatch between the existing culinary technology and the new operational realities of the industrial age. The American breakfast table was waiting for a breakthrough. The breakthrough came not from a food company or a commercial kitchen, but from a laboratory at the New York Botanical Garden. The year was 1901. The scientist was Dr. Alexander P. Anderson, a botanist and plant physiologist, whose objective was not culinary innovation, but pure academic inquiry. He sought to understand a fundamental property of plant life, the precise location and behavior of water within individual starch granules. To do this, he devised a simple, direct experiment. He would isolate starch, in this case from rice grains, and subject it to intense heat and pressure to force out the internal moisture for measurement. His chosen vessel for containing this reaction was a set of thick-walled, hermetically sealed glass tubes. The protocol was straightforward. Anderson placed a small quantity of the prepared starch into a glass tube, sealed it, and began heating it in a laboratory oven. As the temperature inside the tube climbed far past the boiling point of water, the trapped moisture within each microscopic granule began to transform. The internal pressure built to a staggering level, estimated later at over 100 pounds per square inch. Anderson was not weaponizing grain. He was simply applying the principles of thermodynamics to a biological specimen. But the structural integrity of the glass was being tested against a physical force it was never designed to withstand. The pressure reached its critical limit. The resulting failure was catastrophic. The glass tube did not merely crack, it exploded with a sharp report, shattering into hundreds of fragments. Once the dust settled, Anderson examined the wreckage of his failed experiment. But amidst the debris he discovered something that was not a failure at all. The starch granules were gone. In their place lay a pile of white, porous and vastly larger structures. The sudden, violent drop in pressure upon the tube's rupture had caused the superheated water within each grain to flash boil into steam, expanding with such explosive force that it turned every single granule inside out. The starch had puffed to nearly 10 times its original volume. Anderson had not succeeded in measuring the water content of starch. He had accidentally discovered the foundational process for an entirely new industrial food. The accidental discovery in the wreckage of his laboratory represented a fundamental pivot for Anderson. His initial objective, the precise measurement of moisture in starch, was immediately abandoned. The new objective was far more ambitious: to control and industrially replicate the violent, transformative physics he had just witnessed. The problem was no longer one of botanical science, but of mechanical engineering. The shattered glass tubes demonstrated with catastrophic clarity that his existing apparatus lacked the structural integrity to contain the forces involved. Glass, with its low tensile strength and brittle nature, was an instrument for observation, not a vessel for high-pressure industrial processes. What Anderson needed was a material capable of withstanding the equivalent of a controlled detonation. The answer was iron. His next series of experiments marked a deliberate transition from the laboratory bench to the workshop. He abandoned fragile glassware in favor of heavy, thick-walled cylinders forged from cast iron. Each cylinder, measuring approximately 10 inches in length with a 3-inch bore, was designed not to be observed, but to contain and direct immense energy. The hermetic seal, previously achieved with fused glass, was now accomplished with a massive threaded steel plug at one end, tightened with a heavy wrench to ensure a pressure-tight fit. This was not an instrument of delicate measurement. It was a crude, industrial pressure vessel, the direct ancestor of the cannons he would later exhibit. The strategic objective had shifted from understanding the puffing phenomenon to harnessing it as a reliable manufacturing tool. This period became a hazardous exercise in trial and error. Anderson would load a cylinder with rice, seal the plug, and place the entire apparatus into a large gas-fired furnace. The critical challenge was managing a complex matrix of variables. The temperature had to be raised to a precise point, later calculated to be approximately 550 degrees Fahrenheit, to turn the internal moisture of the grain into superheated steam. The pressure had to build to a critical threshold of over 200 pounds per square inch. But the most difficult variable was the pressure release. Too slow, and the grains would simply cook. Too fast, and the explosive expansion was guaranteed. Using a quick-release locking mechanism of his own design, Anderson would unseal the cylinder, which discharged with a deafening report. The results were wildly inconsistent. Early trials yielded little more than scorched, inedible pellets. Others produced a mixture of perfectly puffed kernels alongside charred, carbonized masses. The violence of the process was unforgiving. Yet through this dangerous and often frustrating process, Anderson was methodically mapping the operational parameters of his discovery. Each failure, whether a burnt batch or a ruptured seal, provided critical data. He learned the exact moisture content the grain required, around 14%, and the precise duration of heating needed to achieve uniform pressure without scorching the product. He was no longer a botanist stumbling upon an accident. He was an inventor, reverse engineering a physical event. The small, robust iron cylinders proved that the explosive force of flash-steamed water could be contained and, most importantly, released on command. The principle was now proven. The challenge was no longer one of discovery but of industrial scale. Anderson's iron cylinders had proven that the explosive force could be contained and released on command. But the true drama of the process was not in the workshop furnace. It was microscopic, taking place within the cellular battlefield of each individual grain. The explosion puffing which Anderson had perfected was not a chemical reaction. It was a feat of pure physics, a process where the fundamental laws of thermodynamics were weaponized to trigger a controlled, catastrophic failure of the grain's own internal structure. The entire operation was predicated on a single powerful principle, the violent expansion of water as it flash boils from a superheated liquid into a gas. Inside the sealed cannon, as the temperature climbed towards 550 degrees Fahrenheit, the pressure simultaneously escalated to over 200 pounds per square inch, more than 13 times normal atmospheric pressure. Under these extreme conditions, the kernel's internal moisture, typically between 12 and 14% by weight, behaved in a way that defies conventional experience. It did not boil at 212 degrees. Instead, constrained by the immense pressure, the water became a superheated liquid, storing a tremendous amount of thermal energy. At the same time, this intense heat and pressure worked on the grain's starchy endosperm, gelatinizing the tightly packed granules and transforming the hard, brittle interior into a soft, pliable, almost molten state. This softening was a critical precondition for what was to come. The climactic event was the instantaneous release of that pressure. The moment the cannon's muzzle was unsealed, the external pressure dropped from over 200 pounds per square inch to the standard 14.7 pounds per square inch of the atmosphere in a fraction of a second. For the superheated water trapped within the grain structure, this was a containment breach on a molecular scale. With the external constraint eliminated, the water immediately flashed into steam, expanding with a speed and violence that is difficult to overstate. A single cubic millimeter of water, when converted to steam, will attempt to occupy a volume over 600 times larger. The process was not boiling, it was a detonation. This explosive force, originating from countless points within the kernel itself, acted upon the now plasticized endosperm. It inflated the grain from the inside out, stretching the softened starches into a delicate, porous latticework before they could cool and harden. The result was a complete physical metamorphosis. A hard, dense kernel of rice was transformed into a puffy, airy structure, 8 to 10 times its original size. The process also perfectly cooked and toasted the grain, driving off nearly all the remaining moisture and rendering it completely shelf-stable. Anderson had not just invented a new food product, he had successfully engineered a way to turn the physics of phase transition into a reliable high-volume manufacturing technology. For all the controlled violence of the process, the staggering pressures and explosive thermodynamics, the true validation of Anderson's breakthrough arrived not with a deafening report, but in a moment of quiet sensory analysis. Following one successful test after the cloud of steam had dissipated and the puffing cannon had cooled, he examined the contents of the receiving cage. What lay before him was not the inconsistent mixture of scorched failures and partially transformed grains that had defined his earlier trials. It was a uniform mass of brilliant white, perfectly formed kernels, each one a testament to the now mastered physics. Mechanically, the process was a proven success. The kernels had expanded to the desired volume, between 8 and 10 times their original size. Their moisture content had been reduced to a negligible level, approximately 2%, ensuring their shelf stability. But the decisive test was not mechanical, it was culinary. Anderson took a single puffed grain and placed it in his mouth. The result was not a scientific data point, but an immediate, unambiguous revelation. The structure was incredibly light, a friable lattice of starch that shattered with a distinct crackle. It was not hard or chewy, but crisp and airy, a material that seemed to be composed more of voids than of substance. Then came the flavour. It was not the raw, grassy taste of uncooked rice, nor the simple sweetness of boiled grain. The explosive heat of the puffing process had imparted a subtle, pleasant, toasted character, a clean, nutty flavour entirely distinct from any other food product. It was in this moment that the entire enterprise pivoted. The years of academic inquiry, the shattered glass tubes, the dangerous experiments with iron cylinders, all of it had been premised on understanding a physical phenomenon. But what Anderson now held was not a scientific specimen, it was food. More than that, it was an entirely new category of food, one that was shelf-stable, required no preparation, and offered a completely novel texture and flavour. The problem of how to measure water in starch was forgotten. The new, far larger objective was now terrifyingly clear: how to supply an entire nation with a product it did not yet know it wanted. The scientist had become an inventor. The laboratory experiment was now a consumer good. With his process patented and the product's culinary superiority confirmed, Anderson took the logical next step. He presented his invention to the undisputed command staff of the American breakfast industry, the leadership of the Quaker Oats Company. The year was 1905. Inside the corporate headquarters in Chicago, the inventor laid out the strategic case for his puffing guns. He presented not as a salesman, but as an engineer detailing the operational capabilities of a new class of weapon. He explained the physics, the controlled detonation that transformed hard grain into a light, crisp, and shelf-stable, finished good. He demonstrated the product itself, a food with a texture and flavour profile for which there was no existing market equivalent. Crucially, he offered them a patented proprietary technology that perfectly filled the strategic gap in the American morning meal. The leadership, under the direction of the company's chairman Henry Parsons Crowell, listened with professional courtesy. But what they heard was not a breakthrough, it was an aberration. For an institution whose entire industrial might was built upon the methodical, high-volume doctrine of milling, of grinding, cutting, steaming, and rolling oats, Anderson's process seemed less like a manufacturing revolution and more like a theatrical gimmick. Their vast Cedar Rapids plant, the largest cereal mill in the world, was a monument to the principle of reduction. Grain went in, and a denser, flaked or ground product came out. Anderson was proposing a doctrine of explosive expansion. The very nature of the technology was alien to their operational mindset. They envisioned the logistical nightmare, batteries of roaring cannons, the complex management of steam pressure, the inherent violence of the process. It did not align with the clean, controlled, and almost silent grind of their steel rollers. They saw a fairground novelty, a process suitable for the spectacle of a world's fair, but fundamentally unsuited for the serious, industrial-scale production of a staple food. The psychological gulf was too wide. They were masters of a known universe, and Anderson was describing a new one. This institutional cognitive bias resulted in one of the most significant strategic miscalculations in the history of the food industry. Faced with an opportunity to control an entirely new product category, the leadership of Quaker Oats saw only noise, risk, and a deviation from their core business. They failed to grasp the strategic implications of a food that required no cooking, possessed an indefinite shelf life, and offered a completely novel sensory experience. The decision was polite, unambiguous, and in retrospect catastrophic. They were not interested. Battle Creek, Michigan, 1905. At the same time, Anderson was facing a strategic dead end in the corporate offices of Chicago. A second front in the war for the American breakfast was being waged from an entirely different theatre of operations, under a completely antithetical doctrine. Its commander was Dr. John Harvey Kellogg, the charismatic, autocratic superintendent of the sprawling Battle Creek Sanitarium. Here, the breakfast problem was framed not as a question of industrial efficiency, but of medical pathology. Kellogg was waging a war not against lengthy preparation times, but against what he termed auto-intoxication, the theoretical poisoning of the body by the putrefaction of undigested food in the colon. His entire philosophy of biologic living was predicated on digestive health and the absolute necessity of gentle food processing. Where Anderson's method represented a violent, instantaneous application of extreme heat and pressure, Kellogg's was a slow, meticulously controlled, and almost clinical procedure. His innovations, like the original cornflake, stemmed from a belief that food must be thoroughly pre-processed through careful cooking and mechanical breakdown before it ever reached the human digestive system. His process began with whole grains, which were first steamed for several hours to fully gelatinize their starches, then tempered to equalize internal moisture. They were then fed not into a cannon, but between a pair of enormous water-cooled rollers. These flaking mills, exerting immense but consistent pressure, mashed the softened grain into a paper-thin sheet which was then carefully scraped off and baked into a delicate, crisp flake. The contrast in industrial philosophies could not have been more stark. Anderson's workshop was a foundry, harnessing the physics of a controlled detonation to achieve explosive expansion. Kellogg's food production facilities functioned as extensions of his medical laboratory, designed to execute a therapeutic protocol through methodical, gentle transformation. Anderson had weaponized steam, Kellogg had weaponized digestion. These two approaches, one born of accidental physics and the other of rigid medical theory, now represented two entirely separate competing technological lineages, both aimed at capturing the same strategic prize, the American breakfast table. But while Kellogg's medical doctrine was rigid, the day-to-day operations of the sanitarium's food laboratory were defined by constant, often hurried experimentation. And it was here, in the gap between prescriptive theory and operational reality, that an accident would give birth to a process that would prove just as revolutionary as Anderson's puffing guns. The inciting incident, according to company history, occurred sometime in 1894. A batch of boiled wheat, the base material for a new digestive bread, was prepared for the rollers. But a procedural oversight, a forgotten task amidst the relentless demands of the sanitarium, left the cooked wheat sitting out for several hours, far longer than the standard protocol allowed. Normally, such a delay would condemn the batch. Left to cool, the gelatinized starches would congeal into a dense, unworkable mass, useless for the flaking rollers. But when Will Keith Kellogg, John Harvey's younger brother, and the institution's pragmatic business manager inspected the forgotten material, he observed something unexpected. The wheat was not a sticky, solid lump. The prolonged rest had allowed the internal moisture to distribute with perfect uniformity throughout each grain, a process that would later be understood as tempering. On a whim, instead of discarding the batch as waste, WK ordered it run through the rollers. The result was a profound departure from all previous outcomes. The rollers, instead of mashing the wheat into a single doughy sheet, caught each perfectly tempered grain individually. The pressure was applied not to a mass but to a kernel. It did not produce a sheet of dough. It produced distinct individual toasted flakes. Each grain was flattened and cooked into a single, crisp, self-contained unit. This was not a minor variation. It was the discovery of an entirely new manufacturing principle. The accident demonstrated with startling clarity that the key to a perfect flake was not the cooking, nor the rolling, but the previously unappreciated science of tempering. With this single, accidental batch, a competing food technology had been born, one based on the patient chemistry of moisture equalization, a direct industrial rival to the violent physics of explosive puffing. These two rival technologies, born from laboratory accidents less than a decade apart, represented two fundamentally irreconcilable industrial doctrines. Each process was aimed at the same strategic objective, the creation of a light, crisp, ready-to-eat cereal, but they arrived there via entirely opposing philosophical and physical paths. One was a doctrine of explosive violence, the other, a doctrine of gentle persuasion. Anderson's puffing was a thermodynamic event. Kellogg's flaking was a biochemical one. The puffing process was an act of pure, overwhelming force. It was predicated on a contained detonation, a direct physical assault on the grain's structural integrity. Its core principle was the instantaneous, violent expansion of superheated water, a force that turned the kernel inside out in a fraction of a second. The resulting texture, a light, airy and porous lattice, was a direct artifact of this explosion. The grain was not so much cooked as it was shattered and reconstituted by raw power. It was a product born of pressure, heat and speed. The flaking process, by contrast, was an exercise in patience and control. Its success depended not on violence, but on the slow, methodical management of the grain's internal state. The critical phase was tempering, a quiet period of hours where moisture was allowed to migrate and equalize, preparing the gelatinized starches for their transformation. The final act was not an explosion, but a moment of immense steady pressure, a mechanical shearing that flattened the prepared kernel into a thin, brittle structure. The resulting texture, denser, crispier, and layered, was the product of this carefully managed sequence. Ultimately, the schism in technology reflected a profound difference in approach. Anderson, the physicist, treated the grain as an inert object to be subjected to the laws of thermodynamics. He applied an external force so great that it obliterated the kernel's original form and created something entirely new. Kellogg, the physician, treated the grain as a biological system to be coaxed and guided. He worked with its inherent properties, using time and moisture to unlock a potential latent within the kernel itself. One process created a new food by destroying the grain, the other by perfecting it. These two competing philosophies would now be deployed into the open market, launching the first great war of the American breakfast table. The rejection from Quaker Oats was not a defeat for Anderson, but a clarification of his strategic objective. The leadership in Chicago had not seen a product. They had failed to see a viable industrial process. His demonstration cannons at the World's Fair, for all their theatrical impact, were artisanal tools. He had proven the physics, but he had not yet proven the logistics. The new front in this campaign would not be waged in a corporate boardroom, but on the factory floor. The central problem had become one of scale, to convert a single hand-operated puffing gun into a reliable, high-volume production battery, proving that his process was not a novelty, but a revolutionary manufacturing system. This proof would be funded by a smaller, more aggressive competitor. While Quaker dominated the traditional oats market, the American Cereal Company of Minneapolis recognized it could not win a direct engagement on milling capacity. It needed a new class of weapon to outflank the established giants. Presented with Anderson's puffing technology, their leadership saw not the operational risk that Quaker had, but the strategic opportunity. They saw a proprietary, patented process that could open an entirely new front in the breakfast war, one for which their larger rivals had no existing doctrine or equipment. In 1905, they made the wager Quaker would not, forming a partnership to finance the construction of the world's first puffing gun factory. The inventor now had his industrial patron. The real engineering work could begin. The challenge was monumental. Anderson's original cannons were little more than bronze prototype barrels, roughly 20 inches in length with a 3-inch bore, designed for a single operator. To achieve industrial-scale output, the new cannons had to be transformed into massive, durable pressure vessels. The design shifted from bronze to heavy-duty cast steel, with barrel lengths extending to nearly 6 feet and bores widened to 6 inches, increasing the payload of a single cannon from a handful of grain to over 20 pounds. Where the original cannons operated at an estimated 200 pounds per square inch, the new factory models were built to the standards of industrial steam boilers, engineered to safely and repeatedly contain pressures exceeding 500 pounds per square inch. This was a critical safety requirement. A failure in a battery of 24 cannons would not be an accident, but an industrial catastrophe. But the most complex problem was not size or strength, but the creation of a reliable, semi-automated system. The factory environment demanded a level of precision and consistency that manual operation could never provide. The solution was a mechanical ballet of unprecedented design. Anderson devised a system where the cannons, now weighing several hundred pounds each, were mounted on a massive, slowly revolving turret. This carousel would carry each individual cannon through a precise sequence of stations. Automated loading with a measured charge of grain, passage through a long tunnel-like gas furnace heated to a uniform 550 degrees Fahrenheit, arrival at the firing station where a mechanical trip latch would release the breech plug, and finally a cooling and cleaning cycle before reloading. The entire operation was a matter of industrial choreography, turning a violent, discrete event into a steady, rhythmic and profitable process. Anderson was no longer just an inventor. He was a systems engineer building the assembly line for an explosion. The first full activation of the Minneapolis production line in early 1906 was not a launch. It was a trial by fire. The blueprints and prototypes from Anderson's workshop were now realized in hundreds of tons of cast steel and brick. The rotating turret, a carousel of 24 massive puffing guns, was set into motion for its first continuous performance test. This was the moment where theoretical capacity would confront the unforgiving physics of high-volume industrial operation. The factory floor was no longer a construction site. It had become a proving ground, a laboratory for measuring the brutal realities of turning a controlled explosion into a commercial product. The sensory assault was immediate and overwhelming. The sound was not the single sharp report of Anderson's early experiments, but a relentless rolling barrage. With the turret completing a full rotation every 3 minutes, The system was designed for a cycle time of one detonation every 7.5 seconds. The result was a continuous overlapping thunder that physically shook the building's foundation. Each cannon discharged with a concussive blast that reverberated through the chest, a sound so loud that unprotected human communication was an impossibility. Engineers and workers, armed with clipboards and stopwatches, learned to operate in a choreographed silence, their world defined by the violent rhythm of the machine and the shimmering heat radiating from the furnace tunnel. The data collected in these initial runs painted a grim picture. The challenge was threefold: consistency, yield, and safety. Consistency proved to be the most immediate failure point. While the automated system ensured each cannon received a uniform charge and heating time, the output was wildly unpredictable. A successful cycle would shower the collection bin with a perfect cloud of uniformly puffed rice. The next might produce a shower of dense, unpuffed duds, kernels that had failed to detonate. The next, a cloud of blackened, scorched pellets, the result of a fractional overexposure to the 550-degree heat. Initial success rates, defined as a charge producing over 90% perfectly puffed kernels, struggled to surpass 70%. This inconsistency translated directly into a catastrophic problem of yield. Every failed detonation represented a complete loss of the 20-pound charge of grain. The implications were not merely qualitative, they were brutally mathematical. A 30% failure rate meant that for every 1,000 pounds of raw material that entered the system, 300 pounds were immediately converted to waste, along with the proportional cost of the natural gas used for heating. Profitability was impossible under these conditions. Furthermore, the safety implications were terrifying. Each of the several thousand detonations per shift tested the structural integrity of the cannons and their breech plugs. A single failure of a pressure seal or a hairline fracture in the barrel would not be an incident. It would be shrapnel. They had successfully built the machine to weaponize steam. The new, far more difficult war was against the machine itself, a battle for reliability, efficiency, and control. St. Louis, 1904. Even as Alexander Anderson prepared his battery of puffing guns, a second, far more conventional front in the breakfast war was being waged from within the monumental palace of manufactures. There, the Kellogg Company, now officially detached from John Harvey's sanitarium and driven by the commercial ambition of his brother Will Keith, had established a beachhead. Their exhibit was a model of the doctrine that had created it: clean, orderly, and clinical. Attendants in crisp white uniforms stood behind long tables, methodically handing out small paper cups containing samples of their newly perfected product, Kellogg's Corn Flakes. The pitch was rational and direct, focused on health, convenience, and the unique, crisp texture achieved through their patient process of tempering and flaking. This was a ground campaign, an attempt to win over the public one consumer at a time through logical appeal and sensory evidence. But their methodical, quiet stand was about to be completely overrun by the industrial shock and awe campaign being deployed just a short walk away. When Anderson's puffing guns began their demonstration, the series of percussive booms that echoed across the fairgrounds acted as an acoustic summons. The sound, a rapid concussive volley that physically registered in the chest, drew crowds by the thousands. They abandoned the quiet, orderly exhibits to witness a spectacle that seemed to promise not just a new food, but a new kind of industrial magic. What they saw was theatricality on a scale the food industry had never before attempted. The sight of the 8 cannons firing in sequence, the explosive discharge of billowing white clouds, the sheer volume of product created in a single, instantaneous detonation. It was not a sales pitch. It was an event. People did not simply sample the product, which was now being marketed as puffed rice and puffed wheat. They were consuming the story of its creation. The slogan that soon accompanied it, "The food shot from guns," was not a marketing contrivance. It was a literal, visceral description of the process the public had just witnessed. The contrast in marketing doctrine was absolute. Kellogg offered a food. Anderson offered an industrial spectacle. While the Kellogg representatives explained the benefits of their flakes, Anderson was firing them out of cannons. This was not a competition of products. It was a competition of narratives, and Anderson's was louder, more dramatic, and infinitely more memorable. The puffing guns became the single most talked about exhibit at the fair, a successful field application that demonstrated a new powerful principle. The manufacturing process itself, when sufficiently dramatic, could become the most potent marketing weapon of all. The American cereal company's wager had paid off. They had not just presented a new product, they had seared its creation story into the public consciousness with thunder and steam. The victory at the World's Fair was not measured in sales, but in the capture of the public imagination. The marketing slogans that emerged from the spectacle, the food shot from guns and the eighth wonder of the world, were not merely clever advertising. They were a successful psychological operation that fundamentally reframed the category of ready-to-eat cereal. Before 1904, cereal was either a bland utilitarian porridge or a medically inflected health food championed by ascetics like John Harvey Kellogg. Anderson's process, and the theatricality used to promote it, shattered this perception. It transformed breakfast from a matter of domestic routine or digestive theory into a direct engagement with industrial power and technological wonder. This shift in perception was critical. The American consumer of the early 20th century was enthralled by the grand narrative of progress. It was an era defined by staggering feats of engineering: the transcontinental railroad, the first automobiles, the harnessing of electricity, the looming promise of the Panama Canal. The puffing gun, with its explosive report and its transformation of mundane grain into something entirely new, situated Anderson's product squarely within this context of industrial magic. To eat puffed rice was not just to have a convenient meal, it was to consume a piece of the modern age, to participate on a domestic scale in the same forces of heat, pressure, and mechanical ingenuity that were reshaping the world. The psychological impact was therefore decisive. Kellogg offered a food developed through a quiet, clinical, and somewhat esoteric theory of biologic living. Anderson offered a food born of fire, steam, and thunder, a product whose very existence was a spectacle. This established an emotional and narrative superiority in the marketplace before the first large-scale advertising budgets were even spent. The American cereal company had secured a powerful beachhead, not on the nation's grocery shelves, but in its collective consciousness. The battle for market share would not be a simple contest of taste or price. It was now a war of competing mythologies, and one side had just proven its myth was louder, more exciting, and forged in the image of progress itself. The initial factory trials in Minneapolis demonstrated a grim but essential truth. Harnessing an explosion was a problem of industrial choreography, not just brute force. The solution lay not in a single component, but in the radical design of the synchronized production system Anderson had conceived. A deep analysis of this mature machinery reveals a mechanical ballet designed to tame the violent physics of flash-steamed water and transform it into a predictable, continuous, and profitable process. The entire assembly line was, in effect, a single integrated weapon system aimed at the mass production of a novel food. The heart of the system was the massive 20-foot diameter rotating turret, a carousel which carried its complement of 24 6-foot steel cannons through a precise operational sequence. Once automatically charged with 20 pounds of grain, each cannon entered a 40-foot-long brick-lined tunnel kiln. Here, a battery of gas burners, regulated by a series of thermocouples, maintained an internal temperature of 550 degrees Fahrenheit with a variance of less than 10 degrees. This uniform heating, applied over a 3-minute transit time as the turret slowly revolved, was the critical first step in solving the consistency problem. It ensured that every kernel in the charge reached the same internal pressure and gelatinized state simultaneously, creating the necessary precondition for a successful uniform detonation. But the true mechanical genius of the system was found at the muzzle of each cannon, in the design of the quick-release pressure lid. The crude, threaded plugs of the laboratory prototypes were replaced by a robust, cam-actuated breech block. This heavy, precision-machined steel collar featured a set of interrupted threads, allowing it to be locked into place with a quarter turn, forming a pressure-tight seal against a replaceable asbestos graphite gasket, capable of withstanding pressures over 500 pounds per square inch. As the cannon rotated into the designated firing station, a large trip lever on the breech mechanism engaged with a stationary cam on the factory floor. This engagement instantly disengaged the locking lugs. The immense internal pressure did the rest, blowing the lid open in a fraction of a second and triggering the catastrophic pressure drop required for puffing. This mechanism transformed the most dangerous and variable part of the process into a reliable, automated and perfectly timed event, occurring every 7.5 seconds with mechanical certainty. The final piece of the engineering puzzle was the collection system, which had to manage the explosive discharge. Each cannon fired not into open air, but into the mouth of a large hooded expansion chamber. This conical steel housing, measuring 15 feet across, was designed to safely dissipate the blast of superheated steam and kinetic energy. The force of the detonation was vented upwards through a series of filtered smokestacks, while the puffed grains, now incredibly light, were caught in a swirling vortex. They lost their momentum and fell gently through a fine steel mesh onto a conveyor belt below, which transported the finished product to be packaged. This system of controlled expansion and separation made continuous operation possible, turning the chaotic aftermath of an explosion into an orderly flow of finished goods. It was this trinity of engineering, the uniform heating of the revolving kiln, the automated precision of the quick-release lid, and the controlled environment of the expansion chamber, that finally solved the problems of yield and consistency. Anderson had not just scaled up his cannon, he had built a machine that had domesticated a physical detonation. The industrial choreography that domesticated the puffing gun's detonation was a victory of mechanical engineering. Yet the popular image of the process, one that ends with a thunderous report and a cloud of expanded grain, captures only half the story. The product that emerged from the expansion chamber was, in its immediate post-explosion state, fundamentally unstable. Hot, still containing around 4 to 5% residual moisture from the steam, and with its porous structure acting like a microscopic sponge, the puffed grain was highly vulnerable. Exposed to ambient air, it would quickly reabsorb humidity, losing its signature crispness and becoming tough and chewy within hours. The battle for the product was won at the cannon's muzzle. The war for its shelf life had to be fought on a second front in the complex, less dramatic, but strategically critical downstream processes. The first and most critical post-puffing step was drying. The still-warm grains were immediately fed from the collection conveyors into enormous, gently inclined rotary kiln dryers. These were vast steel cylinders, often over 30 feet long and 8 feet in diameter, rotating at a slow 5 to 8 revolutions per minute. Inside, a series of longitudinal flights, or lifters, continuously scooped up the delicate grains and cascaded them through a precisely controlled current of heated air, maintained at a temperature of approximately 250 degrees Fahrenheit. The objective was a feat of delicate thermal management, to drive the final moisture content down from 4% to below 1.5% without scorching the product or fracturing its fragile structure. After a residence time of 4 to 6 minutes in this controlled environment, the grain emerged not just cool, but with a crispness and structural integrity locked in at a molecular level. This process ensured a shelf life measured not in hours, but in months, representing a logistical triumph that made national distribution a practical reality. With shelf life secured, the next evolution was not one of preservation, but of enhancement. By the 1940s, a growing public health consciousness and government-led nutritional campaigns created a new strategic imperative: fortification. The puffing process, for all its physical drama, stripped certain natural vitamins from the grain. To counter this, and to create a new marketing advantage, engineers developed sophisticated fortification systems. Directly after the drying tumblers, the cooled grain passed through an enclosed chamber where it was met by a fine, atomized mist. This spray, dispensed through a bank of precision nozzles, was a carefully formulated solution containing a slurry of essential micronutrients, typically thiamine, niacin and iron, suspended in either a light oil or a quick-drying aqueous base. The engineering challenge was immense: to achieve a uniform coating of just a few parts per million across millions of individual kernels, a task requiring application rates measured in milliliters per minute, without introducing enough moisture to compromise the product's hard-won crispness. This was a process of addition, not subtraction, transforming the cereal from a simple novelty into a scientifically calibrated delivery system for public nutrition. The final transformation was a direct response to the marketplace. While novelty had established the product, the American palate increasingly demanded sweetness. This led to the development of high-capacity coating and enrobing technologies, Puffed grains were fed into large rotating coating pans, essentially massive tilted stainless steel drums resembling concrete mixers. As the product gently tumbled, a precisely metered stream of hot sugar syrup, heated to a specific stage between 235 and 245 degrees Fahrenheit, was sprayed onto the kernels. The continuous tumbling action ensured that each grain was evenly coated, building up a thin, uniform glaze. This was immediately followed by a final pass through a current of cool, dry air, a critical step that flash crystallized the sugar into a hard, non-sticky shell. The cannon provided the volume and texture, but it was this subsequent industrial chain, the tumblers, sprays and enrobers, that delivered a product that was stable, nutritious and perfectly engineered for the consumer. Battle Creek, Michigan, 1906. Inside the headquarters of the Kellogg food operation, a different kind of pressure was building, one with none of the controlled physics of Anderson's puffing guns. It was a pressure of commercial reality, and its force was being brought to bear not on a grain of rice, but on the very soul of the company. Will Keith Kellogg, the pragmatic business manager, faced his older brother, Dr. John Harvey Kellogg, laying out a series of market reports that told an unambiguous and uncomfortable story. The public fascination with Anderson's food shot from guns, ignited at the 1904 World's Fair, was not fading. It was consolidating into a significant commercial threat, a rival doctrine of breakfast that was louder, more exciting, and increasingly sweeter. To counter this, WK proposed a radical and, in his brother's view, heretical maneuver to add sugar directly to their own cornflakes. For Dr. John Harvey Kellogg, this proposal was not a business strategy. It was an act of ideological treason. His entire life's work, the doctrine of biologic living and the war against auto-intoxication, was predicated on the absolute purity of food. Cereals from the sanitarium were not consumer goods. They were therapeutic instruments designed to heal the digestive tract. In his rigid medical cosmology, refined sugar was not a flavoring. It was a poison, a pathogenic substance that directly contradicted every principle for which he stood. To intentionally add it to their product would be to abandon the medical high ground and surrender to the base, corrupted palate of the masses. It was a moral failure, a catastrophic violation of their founding mission. The answer was an immediate and absolute no. But W.K. Kellogg saw the battlefield with a different, more terrible clarity. He was not a physician. He was a manager who had spent decades in his brother's shadow, turning abstract medical theories into profitable, scalable products. He saw the arithmetic of the marketplace, and it showed that novelty and taste were overwhelming the arguments of digestive health. He understood that Anderson's process had permanently changed the psychological landscape of breakfast. The consumer no longer just wanted a convenient or healthy food, they wanted an enjoyable one. His brother's dogmatic refusal to adapt was not a mark of principle. It was a strategic liability that guaranteed their eventual defeat. The choice was irreconcilable. For John Harvey, adding sugar was heresy. For Will Keith, it was survival. This fundamental schism between the two brothers proved to be a command split from which there was no recovery. The disagreement over a single ingredient represented an unbridgeable gulf between two worldviews, one of medical puritanism, the other of commercial realism. Realizing he could never win the war for the American breakfast while serving a commander who refused to use the most effective weapons, WK made a decisive move. In February of 1906, he leveraged his operational control and years of accumulated knowledge to form his own entity, the Battle Creek Toasted Cornflake Company. He secured the exclusive rights to the cornflake manufacturing process, effectively staging a corporate mutiny. It was a declaration of independence. No longer bound by his brother's medical doctrine, WK was now free to wage a new kind of war, one fought not on the principles of health, but on the terrain of mass market appeal, with sugar as his primary ordnance. The corporate headquarters of Quaker Oats, late 1906. The reports arriving on the desks of Henry Crowell and his executive staff no longer described a distant novelty. They detailed a strategic reality that was becoming more alarming with each quarter. The breakfast market, once their uncontested domain of slow-milled oats, was now being carved up by two aggressive, technologically distinct rivals. The data was unambiguous. On one front, Anderson's puffing guns, wielded by the American Cereal Company, had captured the public imagination with the narrative of industrial spectacle. On a second, more conventional front, W.K. Kellogg's new independent toasted cornflake company was waging a brilliant campaign of mass-market appeal, its flakes now fortified with the potent if simple weapon of sugar. For the leadership at Quaker, this constituted a strategic pincer movement on a market they had willfully ignored. The psychological impact inside the boardroom was profound. The comfortable condescension with which they had dismissed Anderson's fairground gimmick now looked like a catastrophic failure of foresight. They had not simply misjudged a product, they had fundamentally misread the direction of an entire industry. The strategic gap they believed to be a niche had proven to be a vast, profitable new continent, and they had allowed two rival powers to establish heavily fortified colonies. The arithmetic of lost opportunity was now undeniable. The response, when it came, was not a gradual shift in strategy. It was a decisive command-level reversal, an act of industrial force designed to correct a strategic blunder through sheer overwhelming power. The time for internal development was over. The objective now was acquisition and domination. In early 1907, Quaker Oats approached the American cereal company not as a competitor, but as a conqueror armed with a checkbook. They purchased Anderson's company, and with it, the exclusive rights to all of his puffing-related patents. The deal was an admission of their initial error, but it was also a declaration of a new war. With the technology now under their control, Quaker's leadership prepared to deploy their most formidable weapon, capital. They immediately authorized an advertising budget that dwarfed anything the cereal industry had ever seen, an unprecedented national campaign designed to flood every newspaper and magazine in the country. Their strategy was clear. They had been outmaneuvered and out-innovated. They would now attempt to win the war not through invention, but through an industrial avalanche of marketing, leveraging their immense financial and distribution power to seize control of the very market they once disdained. The breakfast war was entering a new, far more expensive phase. The opening salvo of this new war was not fired from a puffing gun, but from the printing presses of America's largest magazines and newspapers throughout 1908. Following its acquisition of the puffing patents, Quaker Oats unleashed a marketing barrage of unprecedented scale, committing a budget estimated at over $250,000 for the first year alone, a staggering sum for the era, designed to achieve total information dominance in the American home. The advertising doctrine was a direct extension of the World's Fair spectacle, a campaign of overwhelming industrial noise, full-page advertisements, commissioned from the respected scientist and copywriter Claude C. Hopkins, detailed the physics of the puffing process with the authority of a technical manual. They spoke of grains puffed to 8 times normal size by 100 million steam explosions occurring inside every kernel. The message was one of scientific wonder and overwhelming industrial power. The food was not merely food, it was a technological marvel, an edible artifact of the modern age. Facing this industrial avalanche of marketing, Will Keith Kellogg found himself in a strategically tenuous position. His Battle Creek operation, though profitable and growing, possessed neither the capital for a symmetrical advertising war nor a manufacturing process with the theatrical appeal of exploding cannons. His doctrine of patient tempering and methodical flaking, while industrially efficient, was a quiet clinical process. There was no spectacle to sell. A marketing campaign based on the mechanics of his rollers and tempering bins would be a whisper against Quaker's thunder. Outgunned and outvoiced, W.K. Kellogg understood that a direct engagement on the battlefield of industrial spectacle was unwinnable. He needed to shift the terms of the conflict to fight not a war of process, but of product, not of power, but of trust. The counter-strategy he devised was a masterclass in asymmetrical marketing warfare. Instead of celebrating the violence of manufacturing, Kellogg's advertising focused on the finished product itself, the winning flavor of toasted corn and the simple, natural goodness of the flake. The copy was clean, direct, and centered on the consumer's experience of taste and quality. But the decisive weapon in his arsenal was not a slogan. It was an act of personal accountability. To combat a rising tide of imitators and to draw a sharp contrast with the faceless corporate might of Quaker, Kellogg made a critical decision. He would place his own signature in a bold, flowing script on the front of every single box. This was not a branding exercise, it was a tactical maneuver of profound psychological insight. The signature W.K. Kellogg transformed the cereal box from a disposable commodity into a personal guarantee. In an age of increasingly anonymous, mass-produced goods, it was a tangible link back to the creator, a personal vow of quality from a named individual to every family in America. It bypassed the industrial noise of Quaker's campaign and established a direct, intimate channel of trust with the consumer. It framed the choice for the consumer not as one between two industrial processes, but between an impersonal, explosive spectacle and a wholesome food backed by one man's name and honor. The field of battle had shifted from the factory floor to the printed page. Quaker had deployed an army of scientific claims. Kellogg had deployed himself. The strategic deployments of 1908, Quaker's industrial marketing blitz versus Kellogg's signature of trust, were not abstract campaigns. They were competing doctrines whose effectiveness could be measured with brutal, mathematical precision in the sales ledgers and production reports of a newly born industry. Before the innovations of Anderson and Kellogg, the American ready-to-eat cereal market was a negligible curiosity, a collection of health food products generating less than $2 million in annual sales nationally. By 1912, this marginal category had detonated into an entirely new economic force, an industry with an estimated value exceeding $33 million, equivalent to nearly $1 billion in the 21st century. Quaker's unprecedented $250,000 advertising spend produced tangible, if costly, results. The campaign, which saturated national publications with the spectacle of food shot from guns, successfully purchased a massive share of the public consciousness. By the end of 1909, sales of puffed rice and puffed wheat reached a combined 9 million cases, representing the consumption of an estimated 40,000 tons of raw grain. The puffing batteries in Minneapolis, once a risky prototype, were now operating at near maximum capacity. Their relentless detonations a testament to the brute force effectiveness of a marketing budget that treated consumer awareness as a target to be overwhelmed. For Quaker, the initial strategic miscalculation had been corrected through an industrial avalanche of capital. Yet, a deeper analysis of the operational data revealed a counterintuitive truth. W.K. Kellogg's strategy of quiet trust proved to be the more efficient and ultimately more successful weapon. With an advertising budget estimated at less than half of Quaker's, his Battle Creek Toasted Cornflake Company sold over 11 million cases in the same period, consuming more than 50,000 tons of corn. The patient, methodical process of flaking, lacking the theatrical violence of the puffing gun, delivered a product that captured a larger segment of the American household. Kellogg's personal guarantee, the signature on the box, had forged a bond of loyalty that Quaker's industrial thunder could not replicate. The numbers demonstrated a fundamental disparity in strategic efficiency. By 1912, Kellogg's Toasted Cornflakes commanded an estimated 40% share of the booming ready-to-eat cereal market. Quaker's heavily promoted puffed grains held a respectable 35%. The remaining 25% was fiercely contested by a host of smaller players, including the established, if stolid, grape nuts from C.W. Post. The First War of the American Breakfast was over. Quaker had used overwhelming force to seize a continent, but Kellogg, through a more subtle understanding of the human terrain, had won the more valuable ground. An entirely new industry had been created, not from a single invention, but from the collision of two rival technologies and two irreconcilable marketing philosophies. The market share figures of 1912 represented the definitive outcome of the First Great Breakfast War. The operational data was clear. W.K. Kellogg's doctrine of taste, trust, and the patient chemistry of flaking had proven to be the superior strategy, securing market dominance with greater capital efficiency. Quaker's puffed grains, born of violent physics and propelled by an industrial avalanche of marketing, had seized a vast territory, but it had done so at a stupendous cost. The conflict between the quiet authority of a signature and the deafening roar of a cannon had been decided for the moment in favor of the signature. The two rival technologies, born from laboratory accidents, had collided in the marketplace and in the process had forged an entirely new multi-million-dollar industry from the raw materials of grain, steam, and sugar. But the true legacy of this conflict was not found in the sales ledgers of 1912. It was in the establishment of the two dueling philosophies that would define the processed food industry for the next century. This was the war's ultimate result, a permanent schism in industrial and marketing doctrine, a set of strategic templates that would be copied, refined, and redeployed across every aisle of the emerging American supermarket. The first Great Breakfast War was over, but the operational principles it had validated were now set to conquer the rest of the American plate. The first doctrine was the one forged by Anderson and weaponized by Quaker, the principle of industrial spectacle as marketing. It taught that the manufacturing process itself, if sufficiently dramatic and scientifically framed, could become the product's most compelling feature. The full-page advertisement celebrating 100 million steam explosions created a new kind of consumer desire, not just for food, but for an edible piece of technological progress. This was the birth of techno-food, the transformation of a simple commodity into a marvel of applied physics, a strategy that would live on in every product that touted its micro-encapsulated flavors or flash-frozen freshness. The second counter-doctrine was the one perfected by W.K. Kellogg, the principle of personal trust as a brand. In an age of faceless corporations and anonymous mass production, Kellogg had demonstrated the profound power of a single accountable name. The signature on the box was a deft strategic maneuver, a personal guarantee that bypassed the industrial noise of his rival and spoke directly to the consumer. It established that loyalty could be manufactured not through spectacle, but through the perception of authenticity and quality, a direct bond between creator and consumer. This doctrine would become the foundational strategy for every founder's story and artisan-crafted brand that followed. Ultimately, the collision of these two philosophies did more than create a new product category. It permanently altered the logistical and psychological reality of the American morning. The time-consuming agrarian breakfast of the 19th century, a meal of preparation, was decisively replaced by the industrial breakfast of the 20th century, a product of purchase. The battle was no longer in the kitchen, it was fought on the factory floor and the printed page. Two accidents, one of physics and one of process, had given birth to an industry. Two rival strategies had given that industry its soul. The farm breakfast was dead. The industrial breakfast was born. One shot from a gun, the other signed with a name.